Howdy, folks. I'm Lich, and welcome to my second game devlog. I had originally intended to record this around a month ago, really, but I got really sick at the time, and then it just kind of escaped my mind for a while. But, you know, I'm getting back to it finally. So today we're going to be talking about tile maps because I recently implemented some features that I really want to have in my game, but ended up causing some issues with my also kind of funky art direction. So, in games that normally use pixel art, they will use techniques to avoid some potential issues with rendering it at large scales on high resolution monitors. So, the first trick is to use only integer scaling because this ensures that each texel is rendered by a whole number of pixels when it is drawn to the screen. The second technique is to either ensure that your whatever you're drawing is either snapped perfectly to the screen grid or to use nearest neighbor sampling so that it basically handles that snapping for you. And this allows you to draw pixel art at larger scales on high resolution monitors and still look very clean and crisp, right? That's great, but it's not really what I wanted for my game. I wanted to have different scales and imperfect alignments because I want to have a smooth camera and the ability to kind of zoom in and out and for it to be very smooth transition as you zoom in and out, whereas you pan around. And that doesn't really behave nicely with pixel art for the previously mentioned reasons. So I needed some tricks to kind of fix some of the issues that happen as a result of that. And I've had this kind of playing in the background, and you might have noticed it, but I have two different tile maps here. This left one looks a little bit crisper, but it also has this weird jittering going on as it moves around, and there's occasionally these flickerings of colors bleeding through in the transparent areas around the tile map. This one on the right here, this is using my solution for some of these problems. And it's a little bit fuzzier around the edges, but overall it still looks really good. And more importantly, it doesn't have these kind of weird flickers and jittery motions, which in my opinion are very distracting to look at. And so this kind of eliminates those, which makes it a lot easier to look at and it serves its purpose as a background much better. So if we look at this other tab, I'm rendering the previous scene to a viewport and then scaling that viewport up. And this allows us to look at what's actually happening a lot better. And you can kind of see here as an example between the two that on the left here, we have these texels and the size of the texels are changing depending on the map's position in the world, right? So they get thicker and thinner as it moves around, and that's what causes this jittering. uh, it's very apparent when you look at it at a distance that something's wrong, but this is actually what's happening. On the right here, instead, what's happening is we are kind of blurring and filtering between neighboring texels as it moves around. And this creates a much smoother motion at the cost of also being a little bit blurrier looking. Now, this viewport example is really exaggerated, and I did that on purpose so that you could clearly see what was happening, right? Normally, it's nowhere near as bad, right? This is still annoying to me, but as you zoom out more, the effect gets less pronounced. And if you happen to be at a proper zoom level, so that this isn't the scaling isn't an issue, then it's a lot better. Just overall, it still kind of snaps as it moves, right? So the motion isn't smooth, but the image is clear and doesn't jitter. So this on the left is pixel perfect rendering techniques, and this on the right is what I wanted. And we're going to talk about how I got here. So, first, as just like a quick overview of kind of some of the issues, right? So, there's three main issues that I had run into. So, the first and the kind of simple fix for most cases is what happens when a fragment is on the border of two texels, right? When you're drawing them. So let's pretend this thing here is our fragment. It is a screen pixel, effectively, right? So this is one pixel of our screen. That's what this grid represents. These are our texels, right? It's texture pixels, whatever. This is kind of a multicolored thing, so it's not a perfect example. This big pink block is a little bit better. So what happens, if we're drawing a fragment in the middle of a texel, we can just use the single color. It works great. If we are drawing a fragment in the middle of the two, or kind of overlapping a little bit, if we're using nearest neighbor, we would just get pink here. If we were using a linear filtering, we would get a mix of the two. But linear filtering has some issues, as anybody has, used linear filtering on pixel art has probably seen before. Things get really blurry. And the reason why that is because linear filtering, really what's happening is the UV coordinate is being mapped to the texture. And if the UV coordinate of the fragment that we're going to write, or if its UV coordinate is not perfectly in the center of the texel, then it is going to do a linear filtering and sample from nearby colors, which is what gets this blur effect over here. The problem with this technique is that it doesn't account for the relative size of a fragment and a texel, right? So this fragment is much smaller than the texel here. And so even if it's not in the center, it's still completely contained within the texel. So we only want to draw pink. We don't want to filter. But normal linear filtering will grab colors from this texel over here anyways. So we need a technique that will check if we are inside of a texel, and if so, only sample from that texel. That's a pretty easy thing to do. It sounds a little complicated, but there's a ton of people out there who have implemented solutions for this, right? There's dozens of them available on the web. And I have recommendations for which I think are best. I'll link one in the description that I personally like a lot. But it doesn't work really well when we apply it to tile maps, because tile maps conventionally use atlas textures, which basically is we have a whole bunch of different textures for different things, and we're going to cram them all together into one image so that we only have to load it into the GPU's memory and draw from different sections of that image. And this ends up being a lot more efficient. You don't have to use atlas textures, and you can avoid some of the problems with tile map drawing if you're not using an atlas texture, but not all of them. The specific issue with atlas textures is when we want to draw things, right? So let's pretend, we're drawing, and these are two different texels that we're going to draw to the screen. The issue is if we have a fragment that borders two different texels here, what do we do when either these two different texels are from two different like two different areas in the texture, right? They're not actually neighboring each other, right? One is from, say, this floor tile, and the other one is from this door tile down here. We need to know that these are, not actually adjacent to each other, but that information isn't really easy to get. And the other issue that can happen, and this one is much harder to solve, is what happens when these two texels are from just completely different sources altogether. So that's another difficult thing to solve. And so I'm going to kind of show some of the techniques I've used to overcome this, in addition to fixing some of the other problems that I've encountered. And so one of the other things I'm going to talk about, I'm going to save this more for the end, is mipmaps, because they are much more, their usage is a lot more limited with pixel art. It's very rare to need mipmaps for pixel art assets, but in case you need to use for them, like I did, I'm going to talk about that closer to the end. So here's our atlas texture, and we have kind of two main issues to solve if we're leaving bitmaps for later. We have the issue of, how do we handle the kind of smoothly blending between two different texels when we are at the edge of them and drawing just one color if we're contained inside of a texel. That's easy to do. The challenge then is how do we do this when we are at the edge of two different texture regions that are potentially not even part of the same source texture? So the way I have solved this is through basically taking a tile map, creating a secondary data map texture, which is I'm using an image format, but it's really just a two-dimensional array of extra information about the source and the scale, or sorry, source and the position of a texture region, and using a custom shader that will look into this data map to get extra information about a tile and potentially its neighbors, and then use that to compute the correct color at the boundary of two different tiles, even if they're not in the same tile set atlas. So let's briefly look at the code for that. So this code, I have it up in a public repository. I'll include a link in the description. And this is kind of what I came up to fix this. So first, we have a new node, and this is the Tilemap display node, extends node 2D. This is the kind of base class, so it's abstract. And this class is responsible for generating the data map and other extra information that we're going to pass as uniforms to the shader, right? So it takes a tile map as a parameter, and it is going to kind of scour through the tile map, look at all the tiles, get information about them, such as what their atlas source ID is and what their like offset into the tile region is, what their scale is. It's going to get all that information, store it so that it's available inside of our shader. Then the two different concrete implementations with a mesh-based implementation and a canvas item-based implementation. So the mesh-based solution uses a multi-mesh and draws each tile as a mesh instance. It's just a plain old rectangular mesh that is scaled up to the size of the tile. And the information that it needs to look up into the data map is provided into the instance custom field, um, which we see down here. The canvas item display method instead renders each tile as a unique canvas item that is set as a child of this parent node. And that canvas item also has the same material and set to it. It's got a custom transform. And then the data that we need to look up into the data map is passed as the color of the canvas item, because we can't use instance custom with canvas items, but color does sort of serve as a unique uniform. If you saw my last devlog, you probably heard me mention that there. So we're kind of hijacking the color property of the canvas item to pass information about where to look in our data map. So these two both accomplish the same thing in different ways, and they each have their own little quirks. So I haven't benchmarked, but my assumption is that the mesh-based solution will scale better due to using a multi-mesh. So there's only one canvas item that needs to be drawn, and it uses a single mesh that is just instantiated multiple times with some slightly different data for each instance. The canvas item solution obviously needs to make a whole unique canvas item for each tile, and I'm not really sure what the cost of that is. I'm not very familiar with Godot's engine under the hood. I've only modified it a little bit, and there's still a lot I don't understand. So I don't know how expensive that is, but my assumption is that it is more expensive than the mesh solution, just because it seems like multi-mesh is purpose built for this type of thing. However, multi-mesh cannot be Y-sorted in the same way that you would expect, because all of the different tiles, they're all instances of the same mesh, but they're drawn to a single canvas item, and Godot Y-sorts based off of the canvas items. So if you need Y-sorting, you need to use the canvas item-based solution. So if I kind of go back to my example map here, I actually just have two different nodes here. This one is for the background. This is using the mesh solution. And then this foreground one is using the canvas item one. So you can mix and match them. So if you only need to use, the mesh one, that's probably the better of the two to use. Again, haven't benchmarked. I'll do that at some point, but it's not high on my priority list. Um, canvas item one, you have to use this if you want Y sorting though. So if you have like trees or obstacles, whatever, you want to use the canvas item one. So those are the nodes. And like I said, they collect data about the tile map, store it as uniforms, and pass it to the shader. And the shader, it's a little complex, so we're gonna collapse everything that we don't need to see, and let's take a look at this from a very high level overview. I think, where is our vertex shader? There it is. So the vertex shader here, uniforms, varyings, these are all important. So first off, the uniforms are the size of the tiles, or the base tile size. So 16 by 16 in my case, and this has to be the same across all sources. You can use multiple tile set sources, but it has to be the same base size. That's actually pretty important. You can have tiles that are scaled larger than that, right? So you can have a tile that is maybe a 1x2 or a 2x3 in the atlas, but the base tile size needs to be the same, or else the math gets a lot harder. We then have the sampler representing our map data. So this is just a single channel image that we are going to read from, and what we read is actually going to be data about the tile, not any real color. We have an array of the different sources that we're going to actually get textures from, right? So these are your actual tile sets. And then a simple flag telling us whether or not the data that we want for each tile is inside of the color or the instance custom field. The vertex shader simply reads most of this data out, converts it, and then stores it in some flat varyings so that we have access to them to use down in the fragment shader. So the fragment shader is where the majority of the work is done. So I'm going to expand all this, and actually, it's quite a lot to expand. There we go. So the fragment shader is going to do a couple of things. We are going to first calculate if a fragment is inside of the inner tile region. So if we look over here at this tile set, the inner tile region is like the middle of a tile. And the reason that's important is because if our fragment is in the middle of the tile, even if it borders different texels, we still only sample from that region, right? We don't have to go look into any different regions when we do this filtering. And so our the process of reading is significantly easier. And the vast majority of fragments are going to be in the inner region. In fact, if you even have border fragments, the border can only be one fragment wide. So if they're even present, they're going to be a very tiny minority of the fragments. So that's why we even bother checking, because in the case of being an inner fragment, we want to do the cheaper read process. So I have a dedicated method for single tile sampling. And then if we are unlucky and we're on the border, then we need to do a more complicated sampling method. And so if we go look up here, let's go take a quick brief look. Let's see, this is where they actually are. Let's collapse that. Single tile sample, very basic. We just take the UV coordinate, do a little bit of math to find where we're actually going to read from inside of the atlas texture, and then sample it, right? Get the texels, blend them together. I do some custom blending because how I blend is a little different than just doing a plain linear filter. And there's also some issues with linear filtering and mipmaps. Talk about that later. Now, the multi-tile sample is where things get complicated. So, kind of going back to Godot here, just a visual explanation. So, if we are a fragment, we're going to use the Godot icon as a fragment again, and we border two different texels. The challenge of multi-tile sampling is that these two texels can be from completely different tiles, which may be from different areas in the atlas or different atlases altogether. So what we need to do in this case is not only find, what texels we need to sample from, we also need to calculate where those texels are even going to be located, because they may not be just adjacent to whatever we're sampling from. So what this is going to do is first find the different tiles that we're going to sample from. So this is getting map coordinates. This is actually getting tile data for these tiles. Now, we could be sampling from up to, potentially 4 tiles, maybe just 3 or 2 though. So it's possible that these are duplicates, right? Based off of the math up here. And there isn't really a great way to like not read from duplicates or to handle edge cases without just an absolutely massive function that has a bunch of branching. And it's a shader. I want to avoid branching when I can. I felt that it was worthwhile to do branching down here because so many of the fragments are going to be inside of this hot path, and the multi-tile sampling is our cold path. So I did it down there, but here if we're sampling, it's going to be from either 2, 3, or 4 tiles. We're going to handle it the same way in any case. So we get the tile that is going to be sampled for each of our 4 texels. We then calculate the adjusted texel coordinate, right? Because if we're over here and we're reading from the left side of this texture, we need to read from the right side of this one. So, we need to wrap the coordinate around for for the edge texels that we're going to read. So we get the tiles that we're going to read from, we wrap the coordinate around, then we, actually find the correct area to sample from, and double check just to make sure that we're actually sampling from a valid tile, right? Because there are cases where we might be sampling from, like in this corner, this top left tile, there's nothing here, right? This is transparent. This isn't a valid tile. So we check if our tiles are valid and we mask them out if they're not, and then we blend the colors. So that's how we handle this. It's really simple, like conceptually, but just ends up being a ton of math to actually, you know, do the process of looking up where to sample from, blending everything together. So that's how this node and shader works. And for most use cases, this will probably be sufficient. So if you want to use a tile map and you want to have, smooth, camera motion, uneven scaling, zooming in and out, all that stuff. If you want that type of stuff and you want this look, then that's all you need to know about the shader and the nodes. They're very easy to use. You just plop the node down and assign a tile map to it. So these are the only parameters. It should handle everything else. Um, so mipmaps. Mipmaps are complicated for Atlas textures for another completely different reason. And that's because one, we have the whole texture bleeding thing, right? But two, the size of a tile may not always be the same, multiple uh, as or like scale as the like whole atlas image, right? Let's take an example here. So mipmaps, when you generate them, each mipmap is just half the size of the previous level. And this is done so that if you're reading from something that is either very far away or very small, um, it's you have to read a lot of data to figure out what color a fragment should be, and that's expensive and complicated. It's much easier to instead pre-compute the image at smaller resolutions, um, so that that processing of what data you need, right? We kind of toss out the high frequency stuff, keep the low frequency stuff. That's pre-processed. It's done for you. You just sample from the bitmap. But generating them is kind of where this issue comes in. So let's say this example here. Let's say this is a atlas texture, and each of these colors is a tile inside of it. Let's say this texture is 10 by 10, and so each of these tiles is 5 by 5. Generally, when you make mipmaps, each level is half the resolution of the previous level, rounded, to the next like lowest integer, right? So 10 by 10 would go down to 5 by 5, then down to 2 by 2, right? Not 2.5, because you can't have 2.5 texels. So that's how you would generate them. But we don't care about the image as a whole. We care about the tile regions within the image, and these are 5 by 5. So when we make a mipmap level of this 10 by 10 image, the tiles inside, which are 5 by 5, are going to shrink down to 2.5 by 2.5. And as we just said, you can't have half a texel. So traditionally, like if we were to just generate mipmaps with no custom solution, then the mipmap for these tiles would all of a sudden get, really blurry at the edges. And this isn't it'd be a lot worse than this, but you would get kind of a blending of colors because the bitmaps would be blending together because they would be sharing half a texel. We don't want that. So what we want to do for Atlas texture bitmap generation is if our bitmap level is, being halved in such a way that the tile regions within it are going to be a uneven number in size, then we are only going to use a portion of that mipmap region and draw the tiles as if they were, the next lowest integer. So in the case of these tiles that would be 5 by 5 going down to 2.5 by 2.5, we're going to draw them as 2 by 2 images and then, only use up 4 by 4 pixels of the 5 by 5 map. And so the pixels on the right and bottom edges of the map, they're just going to be transparent. There's no data there. We don't care. So that's how we, correctly generate bitmaps. And then, if we're just careful when generating them to not sample outside of our region, we can avoid bleeding as well. So we generate the bitmaps like that. And I have a custom compute shader that does that. And then when we actually sample from them inside of the shader, we just need to be careful about how we do that, right? So we need to handle sampling from the two different bitmap levels individually. We cannot just use a linear filtering that has a non-integer LOD level because the like region of a texture at one bitmap level may not map perfectly to the same UV coordinates of a different bitmap level if we're using this technique. So we calculate where we need to sample from for each level, sample from them individually, and then perform the filtering ourselves. And so that's how this is handled inside of the actual rendering shader. And the compute shader for this just handles the process of actually making them, right? So it's going to take the original source texture and the size of the tiles within it, and it's going to compute the bitmaps um, basically, the same way I just described. And there is a script that also helps do this for you because it does need some extra information that needs to be calculated ahead of time. It's got to know what tiles are actually being, um, generated bitmaps for, and potentially for tiles that are, scaled larger than 1 by 1 in the atlas. Um, those can have, those bitmap regions, you want to sample between tiles if the tile itself is made up of like, 2, 3, or 4, or whatever, uh, regions of the atlas. So tileset helper script in here uses the compute shader and does that calculation, sets everything up, and generates the bitmaps and produces a texture with the correctly generated bitmaps. So that's how I handled the bitmap solution. And combined together, that's how I get this very smooth looking motion on my tile map without this flickering and jittering. So this was kind of complicated and I kind of rushed through some bits of this. I hope I didn't go too fast or say anything too confusing, but at the same time, I hope I didn't over explain anything that, didn't really need to be explained. I've recorded multiple takes of this because I have a really bad habit of just rambling a bunch, like I'm kind of doing now, but it's the end of the devlog, so it doesn't matter. But yeah, so had this issue with tile map rendering where I was getting all sorts of weird visual jittering and bugs, and I wanted it to be smooth and pleasant to look at. So came up with this really complicated solution that fortunately works and does what I want it to do. So it's still not perfect, and I'm actually going to point out one of the areas that it's pretty flawed at right now, and that's when drawing things on multiple different levels. So if you remember from my example, uh, these are two different levels, and we can see here that the kind of light colored pixels of the tile, above the doorway are kind of bleeding through a little bit here at times. And that's because when these are being drawn, the first layer, right, it doesn't know anything about the top layer, and the top layer doesn't know anything about the bottom one. So when this door is being drawn, the like tile data down here is all transparent invalid tiles. And so there's no, color data to fetch down here to use. Ideally, we would also have information about the previous layer stored alongside the upper layer
so that it can also figure out what to sample from. Um, and I have plans to implement that eventually, but it does add kind of an extra layer of stuff that I need to check for, because now I need to also set the data map. I need to check whether or not a tile is valid because it is actually part of that tile map layer, or if it's part of a different layer altogether. So that is something that can be improved upon. I will eventually implement that, um, but for the most part, it does what I wanted to do pretty dang well. But yeah, that's about it. Thanks for watching, and I hope this was at least interesting to hear about. And if it potentially looks like something that could be useful to you, then I hope that it ends up, saving you however much work it would be to fix it on your own. But yeah, thanks for watching again, and take care.